question number 5. Enable a 250 megabyte swap space on your hard drive. And notice that it has 0 bytes used. Okay, so if you think back to the class on Sunday, what was the key takeaway of class regarding swap space? Can anybody answer? Anybody at all answer? Got a raised hand. Who raised their hand? You just lowered it. Oh, sorry. Oh, no problem. So anybody want to take a stab at, think back to class on Sunday. What was the key takeaway regarding swap space?
I can try. If
yeah, go for it.
I think the explanation was like, basically Linux or Unix uses swap or like disk space as an extension of memory. So there was a concept where, the program thinks that it has unlimited memory, but you have like, only a certain amount of physical RAM available. So hence swap space is used to kind of offload once your memory fills up.
Unfortunately, no. In fact, that is kind of the opposite of the takeaway that we want you to all understand. So let's say you don't have, but good try. Thanks for attempting that, and you're kind of on the right path. So let's clarify. So let's say you have no swap space configured at all. And I probably don't have any here. Let me see. Well, there is, but it's not being used. Okay, or actually, no, there isn't. 0 total. Okay, so let's say you have no swap space being configured at all on your host. Your processes still think they have unlimited memory. It doesn't matter if swap space is there or not. The processes still think they have unlimited memory because Linux, by default, the kernel makes every process believe that it has like tons and tons of memory. That's the virtual memory system. It just gives them tons of virtual memory. Even if you don't have much RAM, they still think they have tons of virtual memory. So actually, in the old Unix days, the swap space was kind of an extension of RAM because RAM was so expensive. But that stopped being the case many years ago, probably 15-ish, 20 years ago. And the use of swap has completely changed the way that it's being used and what the purpose is for. And nowadays, it's not an extension of memory. What it is it's a place for the Linux kernel to park inactively used sections of anonymous memory. So that's the key takeaway from the class, is that swap is for parking very inactive parts of anonymous memory of different programs on the host. And why does Linux want to do that? So the key word there is inactive, and the other keyword is anonymous. So inactive means, let's say you've got a program that's running in memory, and it has allocated some memory for it to use. And it did some calculations or some data manipulation or whatnot in memory, like after it first started up. But then it really didn't need it anymore, and it didn't free up the memory. So that portion of its memory it's not really using it. It hasn't been using it for quite a while, but it's still occupying RAM. It's still occupying your physical memory. And so actually Linux says, well, if it's not being used frequently, it's only just rarely being used, might as well just park it on disk That way we can free up that physical RAM for some other process. And that's exactly what it's for. So that's the key takeaway about swap. Swap is for Linux to be able to park inactive memory. And it's anonymous memory. Anonymous memory. Stuff that's just, the processes aren't really using it anymore. They're holding on to it, but they're not really accessing it. And Linux says, well, if you're not accessing it and you haven't accessed it in quite a while, chances are you aren't really going to be accessing it much in the near future. So I'm just going to park it in disk, and I'm going to free up that physical RAM for other things to use. And so it's done, the reason it does that is for performance reasons. So it makes the fast physical RAM available for other programs to use. And it's strictly for performance reasons. And so that's the purpose of swap space. Did that answer your question?
Certainly cleared my understanding, so thank you.
Okay, Vital, were you the one who guessed the answer a few minutes ago?
Yeah, this certainly cleared my misunderstanding.
Oh, okay, sorry. Yeah. What that means is I must not have explained it good in the class on Sunday. I need to. I probably was trying to rush or something, but yeah, I need to explain that better during the class session. So
this is excellent. I think it brings back some thoughts about okay, basically when troubleshooting back in the days, I probably made some mistakes while interpreting the swap space usage.
Yes, and you know what? I did too, and I think most sysadmins do because we're kind of given the wrong impression about it, and that's a historical thing because the impression we had about it actually was true like way back in the Unix days, but it's no longer true anymore, and so. But there's still a bunch of sysadmins that are still hanging on to the old Unix way of thinking. But yeah, nowadays the swap is just for parking inactive anonymous memory, and to speed up to improve performance.
So I have a question here. So what does it mean if your swap is becoming full?
If your what?
If your swap space, like if your swap is getting filled.
Well, it actually doesn't matter if your swap is full. What matters is this free, you see the screen, my free command?
Yeah.
What matters are two columns here.
Plus used.
No, what matters is
okay.
What matters is free plus buffered cache.
Okay.
If that number, free plus buffered cache, starts getting towards 0, that's when there's a problem. That's when there's a problem because that means you're running out of memory. And swap space has nothing to do with that. Swap space doesn't matter if you have swap or you don't have swap. Do
you mean we should not monitor swap at all?
No, there's really no reason to monitor swap except if you're interested in knowing when your system starts to thrash, what's called thrashing.
Thrashing, yeah.
Yeah, thrashing if your system gets low on memory, which means free plus buffer plus cache starts going down towards 0, then your host is going to start to thrash. And it's either going to thrash on anonymous memory, which means it's going to be thrashing on your swap space, or it's going to thrash in your file cache, your disk. But yeah, if you're interested in knowing when your system's thrashing, you could monitor to see, let's run a VM stat 1. You have two columns here under swap. It's swap in and swap out. If those are both increasing and very, very active, both the swap in and the swap out, that means you're thrashing. It means your host is thrashing. But that's really too late. At that point, you're too late because it means you're running out of memory. And so it's better to be monitoring your free plus buffer cache long before that and and when that starts going down, even before it starts thrashing, you know, if you see this number like historically going down, then you can, you know, you can get an alert for yourself. Does that make sense?
Yeah, thank you.
Okay. Yeah, otherwise there's really no reason to monitor swap. And then, okay, so back to the question. So let's see. Okay, let's go ahead and enable a 250 meg swap space on my hard drive. And we're going to notice that it has 0 bytes used. So let's go ahead and do that. So remember, swap space, whenever you think swap space, think anonymous memory. So I don't have any swap space configured right now. So let me let me create a 250 meg swap file. Well, first let me make sure I have enough space. I did. Okay. I want to make a 250 meg swap file. Here's my swap file. I think I need to initialize it. I can't remember what the command is. Make swap, there we go. And it's telling me I need to change the permissions. So let's do that to make it happy. And then that should be ready to swap on. So let's do sudo swap on. And now if we do a listing, see there, yeah, okay, there we go. So we have a 250 meg swap file, and it's also showing up here in our free -m listing. And you notice how 0 bytes are being used so far in the swap file. Now remember, whenever you're thinking swap file, think about anonymous memory. So how might we start forcing Linux to use that swap file? Well, question 5 here is, so enable a 250 meg swap file. Notice that it has 0 bytes used. Then keep increasing your shell's anonymous usage, as we did in the previous question. After each increment in anonymous usage, check your free usage with the free -m command, and check your shell's anonymous usage with that, where we grabbed that proc file before. So can you think of what 2 things would happen? So before we go to the answer, anybody care to take a guess? We've got a 250 meg swap file. We're going to start increasing our shell's anonymous memory usage by creating variables and stuffing them with like a bunch of data, like 100 megs at a time. And on my system here, I've got 4 gigs of RAM, and only 318 megs are used. So what do you expect might eventually happen if we just keep creating variables with 100 megs of data in each variable? Any guesses? Remember, data that we're putting into a variable is anonymous data.
If nobody wants to guess, I can.
Go for
it. So I think after a point of time when the used memory will fill up, the swap space will start to be used. The anonymous memory will be put in the used swap space.
Okay.
So when we do free-m, we'll see it slowly increasing.
Okay. Let's test it out. So let's go ahead and, well, let's just start. That's the answer, but let's just start testing it out. So the answer here is eventually your shell is going to not be able to allocate any more memory. Because remember, when you're creating variables and you're stuffing a bunch of data into them, every time you do that, the shell has to ask for more memory, right? It's just like as if you're programming in Java, well, not Java, well, yeah, if you're programming in, well, C, for example, or whatever language you're programming in, and you are asking, you're making a call, a system call to ask for memory. Like, let's say you want your program to ask for 10 megs of memory. So in your program, you can ask for that. And so it's the same thing with your shell, your bash. Whenever you're creating variables and you're stuffing data into them, it needs memory for that, and it's going to ask for that memory. And eventually, if we keep doing that, the system's not going to be able to give it any more memory. And so it's actually you're going to run into a cannot allocate memory error. But let's see what happens when we do it. So we're going to do it one step at a time. We're going to create a bunch of different variables one at a time. And after we do each one, we're going to look at our free-min output, and we're going to also look at the grep anonymous memory output here and see how those are affected. So let's start. And so right now, that's what it looks like. And right now, that's what that looks like. So let's create a new variable. And let's call it contents2. Well, anybody can take a guess at what's going to change now on our free-m and also on our proc status. Any thoughts?
Now that you allocated this anonymous memory, it gets decreased.
Let's take a look. So anonymous memory is right here. And it was just 103 megs. Right now it's 205 megs.
So decreased by 100?
So it increased by 100. Yep. Let's take a look at free. Free is showing, what are the differences here? It looks like our free column is about 100 megs more, actually. But our used column is about 100 megs more, right?
Yeah, 318 to 490.
So the used column makes sense. We just increased our usage by 100 megs. But why is the free column 100 megs greater? Any thoughts?
I see it got reduced from the buffer/cache.
Yeah. Any thoughts on that?
I don't know why it did that though.
Yeah. So Linux probably was just doing some juggling under the hood there. And it saw, it's always kind of optimizing things. So it decided for whatever reason it needed to drop some stuff from the page cache. Right. But it could have been its algorithm for doing that. Maybe it was related to our anonymous usage, or maybe not. So it's pretty different though, because remember, buff cache is our page cache, our file cache. So that really has nothing to do with our anonymous memory. Those are two different things. And then really the important number is actually free plus buff cache together is basically our available memory. So let's do it again. Let's increase our anonymous usage even more. And let's do it by 500 megs. So let's make this 500, and let's make a new variable. And this one's going to have 500 megs of data in it. And let's see what happens. And remember, my whole system, I've got 4 gigs of physical RAM. So what we're trying to do is we're gonna get close to using all that. So there we go. We've got 500 megs that is being put into our contents variable. So far, swap space is not being used. This is taking a little while, which might mean that, okay, there we go. So let's check it again. Let's check our anonymous usage. Now what do we expect? We expect about 700 megs. Yeah, there we go, 715. And is our free impacted yet or not? Our use definitely increased. And our buffer cache went down even more. So our used is definitely on the rise. So let's even do it again. Let's create another variable. Let's put a gig of data into this variable. And let's see what happens. This will probably take a minute. And the reason we're using dev urandom is we want to make sure that we have unique data. Because let's say if we didn't do dev urandom, but if we do dev 0 instead, you know what? That's all zeros. And what does that mean? Well, there's a very good chance that Linux would optimize that. It would recognize under the hood, it would recognize that it's all zeros, and it would choose to just say, well, I don't actually have to create a huge variable with all zeros. I just have to create a variable with 1 0 and just put a little flag saying that, you know, it's like, you know, 10,000 of those, right? If you guys aren't familiar with what I'm talking about, are you familiar with the concept of sparse files? Sparse files. Anybody?
I know the data structure, but yeah, maybe similar. I didn't know that Linux actually does that at the shell level.
It might. We don't know. And so we're just making sure that we're having a good test here. Yeah.
Yeah. Solaris had a construct of sparse containers.
Yep. Yeah, sparse is just kind of a way of you know, optimizing your disk usage by recognizing you know, repeated characters and kind of recognizing that you don't have to actually repeat them all and fill up a whole bunch of space. You can just make it's a shortcut. It's a way of making a shortcut where you just say, yeah, there's like 10,000 C characters, but I just have to actually write one of them and then just make a flag saying that there's supposed to be 10,000. Things like that. Okay, so here we've got like a gig. So let's see what happened. Our anonymous definitely is going to be a gig 0.7. Let's see if there's anything interesting going on with swap or free. Swap still is not used. But of course our used memory is going up. And look how Linux is just kind of freeing up the page cache. Why do you think every time we're adding these huge variables into anonymous memory, why do you think Linux is dropping page cache? Any thoughts? Any thoughts on that? Right? So anonymous memory has nothing to do with page cache, right? But for some reason, can you think of why? Okay, we're starting to use a bunch of memory with our anonymous memory. Why would Linux choose to start dropping big chunks of page cache? Go ahead, Sam.
Yeah, it does the housekeeping, right? Just if it is free memory is used is increasing and there is no enough free memory, then it will.
Yes. Yeah. This is Linux getting worried. It's seeing the used memory, it's seeing the anonymous used memory increase. Now remember, anonymous is kind of delicate because it's not backed by any file. So Linux is seeing a bunch of anonymous memory increase, and it's getting worried. It's saying, well, my memory is starting to go down. My free memory is starting to go down. I'd better drop some page cache just to make sure. So that's what it's doing here. So let's do it. So we've really only got about 1.5 gigs. Actually, we've got 1.8 gigs of available memory. Let's make a variable that is let's make it a 1.2 gig variable. Let's see what happens. So once we start getting lower memory, that's when the interesting things are going to start happening. And I'm trying to trigger those interesting things without triggering a whole crash or anything, so that we can see the interesting things happening. So at some point here, we expect to start seeing swap space being used. And it might happen on this one. Because Linux is going to say, whoops, I'm running out of memory. I've already dropped a lot of page cache.
Can we open another terminal and monitor the free space?
Yeah, sure. Let's see, where am I logged into here? Don't remember the public IP for this guy. I could. Okay, I'll run this in the background next time so we can look at it at the same time. Hopefully this will finish in just a second. Or actually, so while we're waiting, I'll open up another terminal. Let's see if I can find the right. There we go. Alrighty. Okay. Let's do a watch. -1, free -7. Again. Wrong buttons. Okay, here we go. We're watching free every second. You can see that use space is climbing. Still no swap space is being used at all. You can see free is dropping. Buff cache is holding steady. At some point, we should probably expect buffer cache maybe to start going down. And also at some point, we would expect swap to actually start being used.
So when this enter free and the buffer both becomes 0, then only it will start using the swap?
No. It'll start. Linux is going to start using it long before that. It's the worst case scenario is free plus buff cache is 0. That means you're already crashed. Linux is crashed. But it's gonna run out of memory. It's gonna consider an out of memory condition even before it gets to 0. Like it'll probably consider out of memory with only even if there's a couple hundred megs in there. So it tries to, it's going to try to use that swap space before that even. So yeah. This is going slow. I'm wondering, wondering if this is a hypervisor. It's stealing. Nope. Nothing's being stolen from this virtual machine. It's just slow. Right, let's go back to our watch. Okay, free is 260. Buff cache is holding steady. Swap space not being used. At some point, some things will happen.
Interestingly, the buff cache is not really going down. The free is rapidly moving.
Yeah, we expect something to happen here soon.
Yeah, maybe you have overdraft protection.
Yeah. Well, swap space is kind of like overdraft protection, I guess. But something might have happened here soon. There we go. Buff cache, page cache is being cleared up. See that?
Yeah.
All right, it has dropped almost all page cache, and it also started using swap space.
Yeah. And on the left side, it shows something.
Oh, and you know what? Actually, it triggered an out of memory for the shell, which we didn't see it happening. I was hoping we would see it, but it crashed the shell. You see how it got logged out? And you see how used memory is like 0. So why is used memory back down to nothing? Because it crashed the shell, and so it freed up all the memory that the shell was using. So yeah, I was hoping sometimes you can actually see that. The shell will show you. Actually, sometimes instead of the shell crashing, it'll throw an error saying like it can't fork, it can't allocate memory.
But here it doesn't give any kind of warning, and it just exited.
Just exited. Let's see if there's anything in more log messages. Towards the bottom here. Yeah, see OOM right there. So we actually triggered an OOM in this case. Right. So we actually triggered the Linux OOM. Is that the right timestamp? I think so. It's February 11th, 04. Yep, we triggered. That must have been ours. Triggered OOM kill.
Yeah.
So that's the worst case scenario. You can see how it tells us that our anonymous memory usage was, when it triggered, was 3.7 gigs. Right here. And it tells us that it was our bash shell. So, yep. In some cases, it doesn't get to that point. Sometimes it'll just kill the shell without going OOM. And other times, like I said, it's kind of interesting because other times it'll actually, I think you can, when I've been experimenting with this before to try to prepare for class, I think if you're getting towards the end and you haven't triggered anything yet, if you do it in smaller increments, like if I reduce the size and I just do like 100 megs for the variable, and I'm just doing smaller increments, I can get it to the point where it'll trigger a fork can't allocate memory and it'll avoid an OM. And that's kind of interesting to see also. Because anything you type over here in your bash shell, the one that you're running, if you start typing stuff like any command, ls or top or just whatever, every one you type, it won't be able to fork it, the command, and so it'll tell you can't allocate memory, can't fork the command. And that's pretty interesting too. And I think I've been able to trigger that by just I'll create those variables, these contents variables. In the beginning, I'll make them big, like I'll just stuff a whole bunch of data. But as memory starts to go down, as the free memory starts to go down, then I'll start slowing down a little, and I'll make them smaller and smaller. That way, I don't trigger the OM, but I do trigger the shell not being able to fork, and that's pretty interesting, to see that. But you can clearly see from that example that you're at the very end there. It starts to use the swap space, and it starts to drop the page cache. It's really trying to do what it can do to keep memory available. And then the final, when it's got no other choice, Linux will kill your processes. It'll do the OM.
Want to become a software engineer at Google? You can, like thousands of our students. You just need to learn from those who've already cleared FANG interviews. At Interview Kickstart, our interview prep courses are developed and taught live by 150 plus instructors from Tier 1 companies like Google and Facebook. Our courses are tailored to help you crack software engineering domain interviews, including back-end, full stack, machine learning, embedded systems, data science, and more. To learn more, book your free webinar slot today